So this is a little video about pressure. Pressure is something that's all around us, but we don't often think about pressure in the context that we think about it in chemistry. So I thought I would start by talking about shoes. So I have these couple pictures of shoes. I want you to notice the difference between this heel and this heel. Okay, in this heel, well, let's suppose that this, let's go over to this heel. Let's suppose that is 1 square inch on the bottom. It's probably a little bit more than that, but we'll suppose it's 1. And suppose you could put 8 of these in the 1 square inch over here. So this area would be 1/8 of a square inch. So in which case would there be more likelihood of doing damage to your hardwood floors? If you have a guest in your house that's wearing shoes like this, or wearing shoes like this. I think we'd probably all agree that these shoes had the potential to do damage to your floor. But let's suppose this lady weighed 100 pounds. If she weighs 100 pounds, is 100 pounds going to do damage to your floor? No, probably not. But if she's wearing a pair of shoes like these, all of a sudden her weight becomes 800 pounds per square inch. So now you notice I put an area on there. The weight really doesn't change. But if she's exerting all of that force over 1/8 of a square inch, then effectively her weight is 800 pounds over that 1/8 of a square inch. So 100 pounds, but it multiplies by a factor of 8 if we do it in pounds per square inch. So often, it even gets worse than this, because often this little pad on the bottom wears off. So you end up with this little bit of a nail head underneath the shoe, and that's even smaller than the pad. So I can show you in my floor where I have little divots from someone who visited who had these little nail heads. And if you ever go to West County Mall, where they have hardwood floors in a mall, you will see thousands and thousands of little divots where normally lightweight people exerted a huge pressure because they exerted their weight over a very small surface area. So that's what pressure is. So pressure is defined as force per unit of area. Whoops, area is EA, force per unit of area. And you find it then by dividing your weight by the amount of surface area over which that weight is exerted. So what is force? Well, in the English system, the force is in pounds. So weight is really just a force. So I'm going to give you some units of pressure. And then I'm going to give you what is normal in our everyday world, which we call standard pressure in chemistry. Okay, so the first unit of pressure we're going to talk about is pounds per square inch. And that's the one that you're used to. If you ever pump up a car tire, you'll see pounds per square inch. That's a B, kind of looked like a 6 when I looked at it. So it's LB, pounds per square inch. So if you ever pump up a car tire, you'll see a pressure gauge measured in PSI. Oh, PSI. So what's PSI stand for? Pounds per square inch. And the atmosphere normally exerts on us 14.7 psi, which means that on every square inch of your body there are 14.7 pounds of force exerted by the atmosphere. So maybe I should define this. When I say standard, I mean standard atmospheric. In other words, the pressure exerted by the air around us. All right, of course, this doesn't look very scientific in terms of what we usually talk about in chemistry, where we talk about use the metric system, and this is the English system. So in the metric system, the unit of force that we use is a Newton. And the unit of length is a meter, so we often talk about pressure in terms of newtons per square meter. Now, Newton per square meter is called a Pascal. Normal atmospheric pressure is 101,300 pascals. Well, that's a big number, so we usually will talk about kilopascals. So I'm going to call that kPa for kilopascal. 101.3 kilopascals is normal atmospheric pressure. So let's talk about what a pascal is. I'm going to draw here a square meter. Try and make it look a little bit three-dimensional. Can you visualize a 1 meter square, not perfectly square, but use your imagination, sitting on the table or on the floor? And then on that square meter we have a little hamburger. So this is a McDonald's quarter pounder. You see a Newton is approximately 1/4 of a pound. So a pascal is one McDonald's hamburger sitting on a square meter. That's not very much pressure, is it? That's why we use kilopascals. Okay, so now normal atmospheric pressure would be 101,300 of these guys. But let's get a little better definition of what a kilopascal is. A kilo means 1,000. So if I have 1,000 quarter pounders sitting on a square meter, you get the idea. That would be a more significant amount of pressure if you had 1,000 of them. That'd be 1 kilopascal. Or you could say that if you have you probably all know somebody that weighs 250 pounds. So if you have a 250-pound guy standing here on the square meter, that would be a significant amount of pressure. So if you visualize this board sitting on your chest and somebody standing on it that weighs 250 pounds, that'd be quite a bit. Well, the atmosphere is 101 of those guys. So 101 guys standing here on this square meter, that'd be a huge amount of pressure. And that's why that can crush so quickly in that little video I did showing you that pressure's all around us. All right, another way to measure pressure in our everyday life is in millimeters of mercury. We measure millimeters of mercury in a device called a barometer. Barometer was invented by a guy named Torricelli, so we sometimes call millimeters of mercury torrs, T-O-R-R. Didn't write that very neatly. Let's do that, T-O-R-R. And here's how a barometer works. So you have a dish or a bowl, and it's sitting here, and then you got inside that bowl you've got a cylinder, and mercury is in the bowl. So all this is, I'm going to color it all in. So show you that's all liquid mercury, and it gets pushed up the cylinder, and once again that's mercury. Mercury is a very dense liquid metal. So in this device, in the top up here, there's nothing. So what's another word for nothing? It's what I created in a can was nothing, vacuum. And the air is pushing on the outside, so however high the air pushes this column of mercury up is the atmospheric pressure. Well, normally, our normal atmosphere will push that column of mercury up 760 millimeters of mercury. And 760 millimeters is 76 centimeters, so visualize a meter stick. I don't have room on my screen to make a meter stick, but a whole meter stick, about 3/4 of a meter stick high, would be normal atmospheric pressure. And then the last unit of pressure that we use normally is atmospheres. Sometimes we just say the Earth has an atmosphere, and the pressure exerted on us we can measure in atmospheres. And normal atmospheric pressure is 1 atmosphere. All right, so we'll need to talk about temperature a little later, but just to quickly sum up what I said about pressure, we know that pressure is force per unit of area. We measure pressure in these units. PSI is what you're probably most familiar with, pounds per square inch. But in the English, that's in the English system, but in the metric system or in science class we use pascals. A pascal is a Newton per square meter. A Newton is about the size of a quarter pounder from McDonald's. Spread out over a square meter is not much. That's why we use kilopascals usually. And the normal atmospheric pressure in kilopascals is 101.3. Remember, 1 kilopascal was this one 250-pound guy standing on this square meter. So the atmosphere has 101 of these 250-pound guys standing on the square meter. So quite a lot. And then other units of pressure that we use commonly in chemistry are millimeters of mercury, or torr. The air pushes this mercury up this column. And if it put 760 is a normal amount of height that the mercury would go to. And then the Earth has only one atmosphere, so standard pressure is 1 atmosphere. All right, so that was the end of this little lesson on pressures.